Hello, these are solutions for homework 3A problem 1. It talks about a particle whose initial velocity is given to us. So using the class notations, I should say, oops, this is a marker. So we have the initial position marked by R with a subscript of 0. This is the same as what we call our initial. Same thing with velocity. V0 is the same thing as V initial. Right. So what are the variables we talk about? We talk about delta t. That's given to us. That is an initial of, it starts at time t equal to 0. And in the problem, it talks about t equal to 1 second. So it's t final minus t initial. So that's given to us. So let me say that's what is given to us. Delta, we usually talk about delta x and delta y. This is a vector now. So we say change in position delta r. So that's r, delta r. That's equal to R final minus R initial. And this is the unknown in the problem in the sense that our initial is given. So this is given. And that is asked for. So the strategy will be that find delta R, which is there in our equations. And then from that, try to find out what is the final position. So that's going to be our unknown. So delta t, delta r, we also have V initial. This time it's a vector. It's V initial. That consists of Vx initial. And there is Y initial. And both of these quantities are given to us. V final in general, that's our Vx final, that direction plus Vy final, and acceleration x I plus ay and j dash. That's our set of equations. Let me clarify what's given to us and what is not given to us. So we have this given to us to be 1 minus 0. That's we are asked for 1 second. It started at t equal to 0. So that's 1 minus 0 seconds. So it's 1 second. That's surely given to us. This is delta x and delta y. That's what we would like to find out. Delta x I plus delta y j. It's not given to us. This is Vx initial is given to us. That's 5.0 meters per second. Let me drop that for it. Drop the units for a moment. So that's 15 j. This is not given to us. We don't know. So let me say that is missing here. Missing variable. It's not appearing in the discussion at all. And acceleration is 0I plus or minus 9.8 meters per second squared J direction. Notice that your x direction separates out completely and the y direction separates out. Correct. And the time is common for both. So that's the way you learn how to do this. One realizes that in the x direction, it is a uniform velocity, that is the motion is happening with uniform velocity because acceleration is equal to 0. So we have a x equal to 0 implies that this is uniform velocity. That implies that delta x is simply going to be equal to v times delta t. It doesn't matter whether it's v final, v initial, since it's delta x, everything is in this direction here. So that's 5 times delta t, which was 1 second. So we immediately get delta x to be 5 meters. 5 meters. This was meters per second, and a second cancels out, so that's just 5 meters. What about y direction? It has an acceleration of minus 9.8, so that's uniform acceleration, and that implies further in this case, since this is a missing variable is v final, we say that the equation that we will use is delta y this time, v initial delta t plus half a delta t square, with the understanding that all these variables are vy initial and ay. This is y and this is vy initial. And that's the equation with the final velocity missing. Plug in our equations. Vy initial is 15 meters per second. Delta t is 1 second plus half times minus 9.8 times delta t square, which is 1 square. So that comes out to 1 square is 1, so that's 4.9. 9.8 divided by 2 is 4.9. Subtract 4.9 from 15. That's about 10.1 meters. We keep the two significant digits, so it's 10 meters. So that's delta y and delta x, but we should be a little careful. We are looking for the final velocities, for final positions here. So delta x is equal to x final minus x initial. And that's given, that we found out is 5 meters. So x final would be x initial for plus 5 meters. And the x initial is given to us as r naught, right? The x component of r naught, that's 2.0 meters plus 5.0 meters. So that's 7 meters. So small work further neater after finding out the change in position. Same thing with delta y. This is y final minus y initial. That's we found out is 10 meters. So that gives us y final is equal to y initial. That's given to us to be 3 meters plus 10 meters. This is meters, and that's equal to 13 meters. So the final position as a solution would be r final. R final would be equal to x final in the I direction plus y final in the j direction. So that's equal to 7.0 I plus 13j, and these are having the units of meters. So it's meters. This is problem 2 in homework 3A. This discusses an aeroplane that is flying horizontally at a speed of 50 meters per second. So an aeroplane flying horizontally, that's important in the sense it is not moving in the y direction. So its velocity is, or it was moving at 50 meters flying horizontally. At 50 meters per second is your problem. So let me work with 60 meters per second. So velocity 60 meters per second. So it's a change from your homework problem, which deals with 50 meters per second. It was at an initial height at so at a height of let's say 200 meters. So again, this in your problem is 300 meters. So I've changed that to 200 meters so that it's slightly varied from the from what you have. So the diagram here will be, so this is a straight line. Let's say that's the ground. And we have 200 meters above the ground will be this dotted line. And somewhere here is our aeroplane. This will keep moving in that direction. That's our, so that will keep moving, but our package will be dropped from the aeroplane and it will move in that direction like this. And the concept here is that it doesn't drop straight down. One would have expected naively, if you're not familiar with what's going on in this chapter, that you drop the package from the airplane here and that will come straight down. But the point is that anything that is moving with the aeroplane, that will have the tendency to move in the same direction until something stops it from doing that. So the tendency of that package will be to go with the same velocity. So it has an initial velocity in the horizontal direction, but right at that point, it doesn't have any y velocity. So that's the information content we have to gather. So let's say that is x direction and y direction. So always try to capture what is the information given to us. So the best is to list everything that we might be looking for. Since it's a projectile motion we are talking about, it is not accelerating in the y direction. So we have no information of acceleration. So this is uniform velocity. So it's good to point that out in x direction. That's uniform velocity. And this is uniform acceleration. How do I know that? Because we are talking about something being dropped in air, and in air, assuming there is no air resistance, we have everything falling at 9.8 meters per second squared vertically, and horizontally there is no acceleration. So that's no acceleration means uniform velocity. So that tells us that the variables we are looking for is uh, is the 5 variables we have been talking about, the kinematic equations, Vy final and Ay. Again, uniform acceleration immediately suggests that this is minus 9.8 meters per second square. What is the, so let's look into the x direction. Delta x here would be this information here in the diagram. So that's delta x. Delta y is the vertical distance that is dropped. So that's delta y. And delta y is given to us. We are told that it is dropped from a height of 300 in the problem it is 300 meters. We said it is 200 meters. And remember, everything we have been choosing is positive in the upward direction. So this makes it minus 200 meters. Delta x is not given to us, even though we do expect it to, again, based on concept that this will move, keep moving in the forward direction. So it's expected to fall somewhere there. But that's what is being asked. How does the horizontal component of the velocity? No, that's not what is being asked. How does the horizontal component of velocity of the bundle change with time during the drop? And the second part is saying to determine the time taken for the drop. So we're basically looking for time t, either from this y direction motion or from this x direction motion. Either way is okay because these are same times. Delta x is not given to us, but we do know the horizontal velocity v here. The package will keep going with that velocity, and it is not going to change that velocity because there is no acceleration in the horizontal direction. So this is 60 meters per second. So a little faster than what is going in the problem. We are also given that at the initial point here, so that initial point is here in the diagram, it is moving horizontally. That means this is 0 meters per second. Right? So that's your all the information that is given to you, and we are interested in delta t in part B of the problem, and how does the horizontal component of the velocity of the bundle change with time. That's part A. So now once we have gathered all this information, now let's try to work on the problem. So let's say this is part A of the problem. In part A, we're not really asked to find the velocity itself. It is just a concept question. It's asking how does the horizontal component of the velocity change. We have already said that this is uniform velocity, so it does not change. So it does not change. That's because it's moving with uniform velocity. So even right before it hits the ground, its velocity, horizontal velocity, will be 60 meters per second. But its vertical velocity is keeping on changing. It will start from 0, and as it falls down, it will keep increasing. So part A is a concept question, and part B now is asking for delta t, determine the time taken. So that's delta t. So it's looking for delta t. We already know we have isolated the y direction separately. We see that there are 3 information given to us, so we can calculate delta t we just have to look for the missing variable, and that gives us the equation to use. That's our missing variable, and the equation that does not have Vy final is delta y is equal to Vy initial times delta t plus half acceleration in the y direction times delta t squared. This is the same equation that we used to have earlier, except that we have changed the variables to Vy initial and Ay here. Plug in the numbers immediately. Minus 200. This is 0 because Vy initial is 0, means the whole term goes away, plus half acceleration is minus 9.8 and delta t squared. That gives delta t. We can calculate delta t now. The negative sign goes away, so it doesn't bother us. So it is delta t squared, so we have to take a square root after we do the algebra. So that's 200 divided by 4.9 using my calculator. And that gives me 6.4 seconds. And that's our delta t, but that's not complete story of part B. It also asks, how will this time change if the airplane was moving faster or slower? Notice what has happened here in all this calculation. This quantity, the horizontal velocity in here, let me draw that in red. Right? This did not contribute to the y direction. Notice, even though it is moving, this is not really contributing to the time that it takes for the vertical direction. Time is happening, that is decided by pretty much the vertical properties of this configuration, and that does not involve the horizontal velocity, so it does not change. So that's a concept. So the question has been asked specifically so that the concept comes out clear that this does not affect this. What it would change is that if I were to calculate delta x, that will get contributions from here. So this is not in the problem, but if we were to ask what is delta x, then you get v times delta t. Right. So that involves the delta t that we calculate. So now we know this is 6.4 seconds, and this is 6.4 seconds, and we don't have any acceleration here, so it's a uniform motion. So that's 60 meters per second times 6.4 seconds. So since I'm not using the units, so let me drop that. So 6.4 into 60. That is equal to 383 meters. Since we are working in two significant digits, we can say that's 380 meters. And we could again ask, how does this horizontal distance that it has traveled change? And that would increase if this were a faster speed, and if it was a slower speed, this will decrease. But the time it takes does not depend on that. So that covers almost everything in the problem. Now let's come to problem 3 in homework 3. It talks about a bullet being fired horizontally with a speed of 500 meters per second at a bullseye, which is exactly at the same level, at a horizontal level. So this is the So let me, for reference, write this is bullet fire at bullseye. Let's change the numbers given here. Let's say bullet speed. And the problem is 500 meters per second. I want to change that to, let's say, 300 meters per second. That's a change. And a horizontal distance. So horizontal distance that it travels. So put that in red. Is the problem given to be 100 meters. Let me say it is 120 meters. And that's a change from the problem. So I highlight that in red. And the rest of it remains the same. Let's say it's still falling under gravity. So the idea is that this is, so let me draw it here. So that's a horizontal distance it would have gone. So that's a straight line path. That's what naively we would think, that if you had a bullet starting from an initial point I, and let's say this is a bullseye. So let me see if I can draw a bullseye. Draw. Let's try this. Yeah, so that's a bullseye. But it doesn't have to really go and hit it at the center, because this bullet will actually fall under gravity. So that's the concept. So let me mark that in, let's say, violet a little. So this will actually take a, oops, I'm supposed to undo, and I'm supposed to draw. So that will actually draw. I'm going to magnify this a little bit. So this is going to draw. Oops. And that's your delta y, right, in our description of motion. So that's your delta y, and that's your delta x in the horizontal direction. Delta x is given to us, but the concept here is that delta y is not 0. So the skill involved is that you don't aim for the bullseye. In fact, you aim slightly higher, so that when it falls in the distance delta x the bullet travels, it should actually hit the bullseye. So let's proceed and see how this will go. Again, x direction, since it's projectile motion, it is going with the uniform velocity. Only 3 variables. Delta x is given to be 120 meters. Delta t, we don't know how much time it takes for the bullet to go horizontally, and at the same time it takes to fall vertically. V initial in the horizontal direction, we know that's the speed of the bullet, initial speed of the bullet. That's 300 meters per second. And delta t, we don't know. Right? And y direction, delta y, we don't know. But what we are asked is, by what vertical distance does the bullet miss the bull's eye? That's a quantity we're looking for. So we immediately point that out. Delta t, again, we don't know. And in the y direction, we have the initial in the y direction, which is 0. This information doesn't appear directly or in an explicit manner in the problem, but the understanding is that since it is fired horizontally, its initial velocity was 0. So that's a concept that went in there. Uh, the final in the y direction, that will be the velocity. So if I were to draw that in the diagram here, so at the final point, its velocity is tangent to the path. Let me try to do that properly. So that's V final. It has both a horizontal direction and a vertical direction. The horizontal direction will be exactly 300 meters per second. It has not changed, but vertical direction, it was 0 initially. It has gained that, but we don't know how much it has gained. So that remains unknown. We don't know what that is. And acceleration in the y direction is falling under gravity. There is no air resistance. So it's minus 9.8 meters per second squared. One might wonder how much the air resistance will contribute, but usually for solid objects like a bowling ball, a stone, the air resistance is significantly lower. So lighter objects that gets affected. So most of these calculations will remain same if you do it within two significant digits. we now notice that there is only two quantities given in the y direction. So we cannot really calculate delta y directly with our knowledge of kinematic equations. So here is where the strategy comes. We notice that there are three variables. Out of the three, two is given to us. So we can actually calculate time. So calculate time, even though that's not asked, and then connect it with the y direction. Right, delta t is the same. Once we know delta t, then we have three information given here to can calculate delta y. So that will be our strategy. So that's a strategy here. For reference is calculate delta t using x information, and then calculate delta y. Once we know delta t, then there is three information given in the y motion. So let's start with delta t. So we do know that next direction is moving with uniform velocity. So delta x is equal to v delta t. Right? V here is vx initial. So that's 120 is equal to 300 times delta t. And that gives us delta t is equal to 120 divided by 30. So that's 4 over 10. So that's 0.40 seconds. I write the 0 at the end so that we have two significant digits. So that's once delta t is given to us. Let me highlight that. So if I were to do that in blue here, now we know this 0.40 seconds for delta t, that's known, and that gives us the information here. That's calculated. And now we have three information on the y direction. What is missing variable is v final y, so that's the missing variable. And that allows us to find delta y. What's the equation we will use since v final is missing? So it is delta y is equal to v initial in the y direction, delta t plus half ay delta t squared. Same equation that appeared in the last problem. Delta y is what we're looking for. The initial y is 0. Again, very similar to what happened last time, in the last problem. plus half AY is minus 9.8, and delta T square is 0.40 square. So using the calculator, 0.4 square into 9.8 divided by 2, so it's 0.784. 0.784 to two significant digits, that's just 0.780 meters, which is about 78, or which is 78 centimeters. That's a good amount of distance. That's almost 1 meter. 1 meter is about 100 centimeters. So the point is 120 meters, which is a good distance away when you talk about a bullet. But since it, uh, or even though it travels at a relatively high speed, because of the distance, it really drops significantly. And what else could we find in here? We could also ask, so now that we have delta y, so this information is given to us, so that's 78 centimeters. Better to keep it in meters, 0.78 meters. We have all the information except the final velocity. One could find that also. The final velocity in the y direction would be equal to v initial velocity in the y direction plus ay delta t. Right, this is not asked in the problem, but just for information, this is 0 plus or minus 9.8, and now that we have the time, that's 0.40 seconds. It comes out negative, that means this is the final velocity here, right? That's your v final in the y component of that velocity. So that's 0.4 into 9.8, and that's 3.9 meters per second. So that's minus 3.9 meters per second. Notice how small this velocity is. So if we were to draw this, so it's very much skewed. Oops. Let me draw this again. So it has an x component, which is very large, and its y component is really small. So the idea here is, let me change the color so that so this is the vector moving this way. That length is v y final, and this length here is vy vx final. That's still going at 300 meters per second, and this is really small relatively, so that's only 3.9 meters per second. Significantly small. So it's almost going horizontally still, but sufficiently large to deviate significantly by almost half the length of an adult body. Right? So that kind of brings out a few of the points in the problem. Let's me pause the recording here, and this is homework 3A problem of 4. We split this homework into 2, so there are 2 more problems which will be covered in homework 3B. This is very similar to problem 3 as far as strategy goes, but it is not a full range problem or even a half range problem. So the details do change. So this is a baseball batter hitting. So let's say a batter hitting a ball in a stadium, and, and let's say its initial velocity has changed in this solution I'm preparing. So initial velocity, and let me change it very slightly because it is really sensitive to the initial velocity there, whether it crosses the fence or not. So let's me change it to 34 meters per second. 3 significant digits is a lot, because 9.8 meters per second square that we use is known only to 2 significant digits. So the third digit here really is not significant in this problem. For that matter, in any of the problems involving projectile motion, the moment we use g to be 9.8 per second, that unless we know the gravity more precisely in Carbondale, it doesn't help much. So so this is 34 is sufficient in here. So let me put that in red, saying, meaning that this has changed from the problem. And let me also say the initial height, I'm going to change, is 1 meter. So that's the height from which position the bat hits the ball. So if you have a taller person, it could be 1.8. If you're shorter, it could be 1. It depends on on where the ball was at the time of hit. So the diagram here is, so let me draw this. So we have, that's your horizontal line. Let me also point out the fact that it is actually slightly off from the horizontal below, because it is hit 1 meter above the ground. So the ball starts from this point, takes a parabolic path, and reaches here. And we would like to stop here, because at some point here, when it reaches delta x, so right underneath that is point delta x, the ground is the red point there. And let me mark that distance as delta x. And that is confined to that, the motion is confined to that region, because this is the horizontal range that we are talking about, is given to be 100 meters away. So the fence that is installed 100 meters away, which is from the ground. And the goal is to find out if this fence really is above the point where this ball crosses, or is it below, right? So there's a possibility that this ball will clear the fence, or it will hit the fence. So we would like to know, this is what we are going to calculate. So let me write that in blue. So this is what we are going to calculate. That's delta y. But this height is the height of the fence, but that has to be subtracted from this height, which is 1 meter. That's 1 meter. So overall, we have to do those subtractions at the end. We'll come back to that. But what we are going to calculate is this delta y, and then eventually analyze whether the delta y is sufficient enough to clear the fence. It's a projectile motion, so we immediately talk about the variables to be delta x, delta t, and v in the horizontal direction. Let me move this over here. So I have an x direction. So in x direction, I have delta x. Go back to black. Delta x, delta t, and vx initial. And in the y direction, I have delta y, delta t, which is common in the two, vy initial, vy final, and acceleration in the y direction, which I immediately say is minus 9.8 meters per second squared. In the starting point, I have a velocity which is tangent to the trajectory, and that's my v initial. That's given to us to be 34 meters per second. And it happens at an angle of, the problem tells you this 45 degrees. Let's keep that to be 45 degrees. So let's not change too many things. So 34 and 45 degrees. And immediately I have to use my vector algebra knowledge. And let me again change this. And this is the horizontal, so that's a vertical component, and that is a horizontal component. Vx initial, Vy initial. The Vx initial is adjacent to the angle, so it is cosine 45. So let me write that down here. So that's 34 cosine 45. And Vy initial is related to the same quantity, so that's 34 sine 45. Notice both came out to be positive because with reference to the point where it is being hit, it is actually in the first quadrant. If it was, if we had drawn our diagram in the opposite direction, then we would have had this negative, and accordingly the numbers would have changed, but the interpretations would have remained the same. So what is this equal to? So let's get the numbers right away. So it's 34 times cosine 45, it is 24 meters per second. Two significant digits. And Vy initial will also be exactly the same because sine 45 and cosine 45 is the same, but in another context where this angle would have been different, these two numbers could have changed. So it's 24 meters per second. So be careful about that in this particular problem, these numbers came out to be the same just because as a coincidence, the angle was 45 degrees. Delta x is given to be 100 meters. So let me put that in. That's 100 meters. And that immediately tells me that, oh, I can calculate delta t from this x direction, very similar to the strategy that we built in the earlier problem. Calculate delta t here. That will let us calculate delta t in there. The moment you know delta t, now there are three information given here, and we were interested in calculating delta y. But once I know delta t, I can calculate delta y, and then there is a small analysis there as to whether delta y is sufficient enough to clear that fence or not. That we'll do at the end. But currently our strategy is to calculate delta y. So let's proceed and calculate delta t to begin with. So let me change to black. So delta x is equal to Vx initial times delta t. That's 100 meters. Vx initial is 24 meters per second times delta t. That gives me delta t to be 100 divided by 24. That's about 4 point something. So in the calculator, say it's 4.2 meters. Sorry, 4.2 seconds. Right? The units of time is in seconds. 24 meters per second, and there was 100 meters. Meters cancels out, and we have 4.2 seconds. So that's my 4.2 seconds. So let me put that in here. So that was not directly given to us, but I calculated that. So it's the same time, which is a coupling factor of these two motions, which are actually a single motion of the ball, but that's being split into the x and y direction in an abstract sense. So now I know delta t is 4.2. I have 3 information. This Vy final is the missing variable, so I use the equation that does not have Vy final, and that's delta y is equal to Vy initial times delta t plus half ay delta t squared. Same equation showed up in the last problem, but now the Vy initial is not 0. That's the big difference, I suppose. So this is 24 meters per second. It's in the upward direction, so that was positive. Delta t we now know is 4.2 seconds. Plus half ay, which is minus 9.8. Delta t squared plus 4.2 squared. So let me put these two numbers separately so that we know whether it is positive or negative. 4.24 into 4.2. So that's 100.8. So let me write that explicitly. So it's 100.8. This is minus. So it's 4.2 square divided by 2 into 9.8. Write that again. 4.2 square into 9.8 divided by 2. So it's 86.4 meters. And that's equal to it's about 14.36 meters. It's 14 meters, let me say. It is 14.4, but we are working in 2 significant digits, so it is 14 meters. Let me remove that dot there. It's confusing. So this is 14 meters. Now we have to still analyze whether it's going to clear the lens or not, fence or not. So that's relatively easier at this point. So let's clarify this clearly. So there is a delta y. Change the color. That's your fence. That's about 10 meters. So that's your fence. And let me also put in a small piece here, which is 1 meter, right? Yeah. So so hopefully this is clear. So this is delta y. This is the height of the fence, which has to be subtracted. Oops, delta y was not that. Erase. So this is delta y. So from this point on, there is slight. So that's delta y. This is 1 meter. Right? That's 1 meter. And all the way down is your 10 meters. So if you want to see how much how much it clears, so this is the amount by which it clears down here. So delta y plus 1 meters, that's the height from the ground, minus of 10 meters is your clearance height. Clearance height. Hope I got that spelling clearance correct. So that's equal to 14 plus 1 minus 10. Right? So that's about 5 meters due to significant digits. And that's the solution. That's the amount of height by which it passes. So the center of ball is exactly 5 meters above the highest point on the fence. I should point out here that it is because the numbers, these are very sensitive to the initial velocity, it is possible that if in the solution, this might hit below the fence. In that case, delta y will not be, so this is height of the fence from the point where it was hit is 9 meters, 10 minus 1. So if your solution to delta y comes out less than 9 meters, that means it hits the fence, and then you have a negative number in there. But that's it's a small analysis that you have to do before you report your answer. I hope this helps. I'll stop here.